All right, hello. Another brief video. We are going to talk about sounds in the cardiovascular system. Uh, you have probably heard about the terms laminar flow and turbulent flow. Uh, Laminar flow is such that when a bunch of things, particles, are all going exactly in the same direction and exactly at the same speed, that means they're not colliding with each other. Um, so you can think of uh, in a road. You can think of with a road with some kind of a road with several different lanes. So the rightmost lane is going to be the slowest. Maybe it's a turn lane or something like that. And then all the cars in that lane are going slow, but they're all going exactly the same speed. Next lane over, you have cars going a little faster, and they're all going exactly the same speed, which is a little faster than the previous lane. The next one, faster still, but everybody's going exactly the same speed. Now imagine that all of these cars are Teslas, and as long as they're all going the same speed in the same direction, you're not going to hear almost any sound. It's going to be silent. The highway is going to be silent, even with thousands of cars going through it. But if something happens, let's say there's an accident, and suddenly there are, instead of 5 lanes, there are one lane left because 4 lanes are taken up by a big tractor trailer that's overturned, and there's still no signs or anything, any warnings. So everybody's going the same speed, and suddenly everybody sees that overturned trailer in front of them, and what is going to happen? Everybody's going to change their speeds, right? And there's going to be screeching of the tires. There's going to be cars crashing into each other. There are going to be cars crashing into their trailer. There are going to be cars crashing into the walls. Uh, Suddenly, the silence of the highway is going to turn into a very, very noisy highway, something that you can hear. The same thing happens in the cardiovascular system. You have blood going through the blood vessels, and there's going to be a layer or lamina of blood that is going to be going right next to the walls inside of an artery or a vein. And that layer is going to go relatively slow. But all the particles, red blood cells, white blood cells, proteins, water molecules, whatever is going there, they're all going the same speed. And they're not colliding with each other. They're not going to collide with the wall, which means they're going smoothly. And then the next layer in, all of those, water molecules and protein molecules and blood cells are going slightly faster. But again, each is going exactly the same direction, again, exactly the same speed. They're not colliding with each other. You go further and further in, and the middle column is going to go the fastest. Again, all of the water molecules, protein molecules, red blood cells, white blood cells, all of them are traveling with exactly the same speed in exactly the same direction. So, what do you expect about to guess about the sound of that blood circulating through that artery or vein? Then it's going to be silent. It's going to be quiet. You won't be able to hear anything. But what if there's an obstruction? Let's say there is an obstruction that you have induced with a sphygmomanometer. You have squeezed with a cuff your arm. And what is going to happen is that suddenly all that blood that is going under particular pressure is going to uh, hit the wall. There's going to be a compression, and suddenly there's a much, much smaller or no outlet for all that blood to go through. So suddenly, all those particles and blood cells and all that stuff, instead of all going in the same speed in the same lane and all going in the same direction, they're suddenly moving direction, changing speeds, crashing, screeching tires, uh, bumping into walls, bumping into each other, bumping into that obstacle that you have made with this manometer. And suddenly that is noisy and you can hear it. And you can hear it with a stethoscope. Stethoscope is going to uh, have a membrane that is going to transfer all of that sound, all those vibrations from that turbulent flow of blood uh, onto the membrane through the whole apparatus into your ears, tympanic membrane, to the three ossicles. Remember the stirrup, hammer, and anvil, and then the cochlea, and you can hear the sound. So turbulent flow is noisy, it's loud. Laminar flow is quiet, it's silent. So when you're measuring blood pressure, you're using sphygmomanometer to, with the cuff to completely close blood vessels. And what sphygmomanometer does and knows is exactly with what pressure it's pressing the artery. And at some point is going to completely close it with a maximal pressure. It's going to completely close it. So once you close it, there's going to be initial turbulence. Whoa, what's happening, everybody's crashing with everybody else, but then there's no more flow, and so the blood just stops. And when everything is stopped, it's silent again, it's quiet. And then you start releasing the pressure really, really gradually. And at some point, instead of being completely blocked off, that artery is going to have a tiny little hole. When you have a tiny little hole, but you have a lot of pressure pushing on it, you're going to have turbulent flow, which means you're going to hear it. What are you hearing it with? You're hearing it with the stethoscope on your arm. Stethoscope is the tool you're using for measuring blood pressure. Sphygmomanometer is just the one that gives you numbers because it knows what pressure it's applying. And so gradually release the pressure in the sphygmomanometer, and you have that turbulent flow. Now remember, it is coming out of the heart, and heart is beating. The pressure is not always the same. It's not smooth. It's coming in bursts. Now each one of those bursts is normally laminar, but now uh, you have burst of higher pressure. So the systolic pressure is going to be high, and it's going to find a tiny little hole too small, and it's going to be turbulent. The diastolic pressure is much, much lower and might be able to go through that hole without making much noise. And so you're going to hear those sounds. And you're going to see those sounds as beeping. You're going to see one and another and another and another and another. Those are Kortkov sounds. And as I usually do, you are going to find in the additional readings a link to the Wikipedia page of Kortkov so you can read a little bit about the guy who discovered this and also made the measurement of blood pressure much easier because you are using the sphygmomanometer plus a stethoscope. So it's the sounds. And then, as you go further and further loosening the cuff. At some point, those sounds are going to stop. All of the, even both systolic and diastolic pressures are going to be uh, unimpeded by any kind of obstruction in the artery, and it's going to have a smooth, laminar, thus silent flow. And once the Kortkov sounds stop, you know you have reached the diastolic pressure. So when the Kortkov sounds start, that is you read off the number on the sphygmomanometer. That's your systolic, and then once the Kortkov sounds stop, you are reading the diastolic pressure. The same thing happens in the heart as well. Uh, normally, I mean, during diastole, the blood seeps or drips from atria into the ventricles, and that is laminar flow, which means it's silent. And then you have a systole, and the ventricles contract. And what is going to happen is that the valves are going to close. Now, valve closing is not instant. It's not like closed, no, open, closed, open, closed, open. No, there is some time, a tenth of a second, 20th of a second, I don't know exactly, that process lasts from completely open valve to a completely closed valve. Uh, and during that time, what is happening, valve is an opening, right? During that period, the opening is getting gradually narrower, 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 narrower until it closes. When it's completely open, you have laminar flow, it's silent. When it's completely closed, there's no flow, so it's silent. But in the meantime, while that opening is closing, uh, there's going to be turbulent flow. All those blood vessels, all those blood cells and protein molecules and water molecules and all that stuff, instead of going all the same speed, all the same direction, are suddenly going to go in a chaotic motion and colliding with each other, colliding with the walls of the valve, and that is going to be producing sound that we can hear. And those are also Korotkov sounds. And those are sounds, heart sounds, that you can hear again with a stethoscope. If it's hearing, it's the stethoscope. So you're going to, use your doctor is going to put a stethoscope on and he's going to hear the lub dub. And you're going to read in your textbook the details when a third or even a fourth sound may appear, and what does that mean, and you need to know that. So Kortkov sounds are sounds that indicate that the blood flow, either in the heart or in the periphery, is not laminar anymore, but is uh, it is turbulent, which means there is an occlusion, which means that the diameter of the passage of the blood has become smaller. And this is what we can use our sense of hearing to detect. Um, we don't need a sense of hearing. Of course, you can use this stethoscope hearing the heart, or while you're hearing while you're measuring the blood pressure, you can hear and you can count, and you can count how many per minute, and you get your pulse. But you don't need a stethoscope for that. Instead of the sense of hearing, you can use the sense of touch. And there are a number of places where arteries are close enough to the surface that you can press them, here and several other places. Again, learn several different places where you're most likely to be able to feel the pulse. And then, in your fingers, in your skin, there are going to be all these, Merkels and Meissners and Pacini's corpuscles that you learned last semester, that are going to send the signals to your brain that you're feeling the pulse. And then you just count how many per minute, if you can. If you cannot, then you can approximate it by counting how many per 30 seconds and multiply by 2, or how many by 15 seconds and multiply by 4, and that's how you get the pulse. And you're then using your finger as your tool instead of the stethoscope, because your finger is going to have touch receptors. The stethoscope is for hearing sounds, which you're going to hear with your cochlea. And sphygmomanometer is just giving you the measure. It's a stethoscope that really measures the blood pressure. Um, See you on Wednesday at the review session. Bye.